Alright, substitution for definite integrals. If you've seen this before, you may already be aware that there are kind of two ways to keep track of things here, or two ways to implement this. Alright, we have an integral here, and we've already learned a little bit about substitution. In here I see u, and then this is almost du out here. So the antiderivative problem would be a type 2 antiderivative, if you remember those different names we gave. Right, that's not very important, but okay. So let's talk about the two approaches here. Method one is just to work out the indefinite integral first. So we're going to go and do a separate problem to find the antiderivative. So our u substitution, x cubed plus 1 du is 3x squared dx, 1/3 du is x squared dx. So in terms of the new variable, I get here u to the 4th times 1/3 du. Taking the antiderivative u to the 4th, I get 1/3 times 1/5 u to the 5th plus c, or 1/15 u to the 5th plus c. The plus c, when we're in the definite integral context, just doesn't matter, all right? Because we can do the use the fundamental theorem of calculus with any antiderivative, including the one where c is equal to 0. So we're just going to take this c here and in the definite integral context set it equal to 0. But now since I started with x's, I need to go back to x's, so I get 1/15 x cubed plus 1 right, to the 5th power. Right. Now that I have my antiderivative, I can go and do the definite integral. According to the fundamental theorem of calculus, this is going to be some antiderivative, any one of them will do, evaluated from x equals 0 to x equals 1. And I've worked out using u substitution what an antiderivative looks like. So leaving the 1/15 out of my way, plugging in 1 here, I get 1 cubed plus 1 is 2 to the 5th power, minus 0 cubed plus 1 is 1 to the 5th power. 2 to the 5th is 32, so this is 31/15. All right. That's the first method. So that method 1, what we're going to do is do the indefinite integral. Okay. Do the indefinite integral first. Right. So we're going to find our antiderivative. And then we're going to use the antiderivative in the fundamental theorem of calculus. Right. Let's look at method 2. Okay. Method 2 is very related, but method 2, we might call this the change of variables approach. In the long run, method 2 is a better way to go. All right. So in method 2, we're going to do the substitution directly into the definite integral. And the difference is that we're going to change the variable, change the limits of integration along with our substitution as we substitute. So I make u equals x cubed plus 1, and as before, I get 1/3 du is x squared dx. Now here's the key difference. All right, these limits of integration are limits on the variable x, and I'm going to do a change of variables. I'm going to change these limits of integration so that now the limits become limits on u. And how do I do that? Well, I look here at my relationship between u and x. All right, if x equals 0, that's my lower limit of integration, then I get u equals 0 cubed plus 1 is 1. If x equals 1, I get u equals 1 cubed plus 1, or 2. All right. And now what I'm going to do is use my u substitution and my new limits of integration to rewrite the definite integral. So my new limits of integration are from 1 to 2, and I have u to the 4th times 1/3 du. Right. Now this is entirely self-contained. I never ever have to return to x's again. All right. Now I just work the new integral, work the new definite integral, so I get 1/3 u to the 5th plus c, I don't care, evaluated from u equals 1 to 2. So we're just applying the fundamental theorem here. So pull the, oops, and I forgot the u to the 5th over 5. My bad. So I get 1/15 u to the 5th from 1 to 2, or 1/15 2 to the 5th is 32 minus 1 to the 5th is 31/15. All right. This way is a little more compact than the other way. And also over the long run, all right, as you do more and more problems, you'll find that keeping track of the substitution and changing the limits of variables on the variables like this is really the way to go. As these problems get harder and as you go on to higher level calculus, sometimes you make more than one substitution, right? And if you were to do that with method 1, you'd have to kind of keep track of everything in your antiderivatives, all right? But if you do that with method 2, when you make a substitution, you change the limits of integration. If you make a new substitution, you change the limits again. You never have to look backward. All right. So my strong preference is that you learn how to do things by this second method here. One more example. All right. In this second example, I'm only going to do it by the second method. So we're going to change the limits of integration. So here I see, I like to rewrite these so they look, so the dx is off by itself, and then we've got a fraction here. So I'm going to make u equals 5x plus 1. So I have 1 over u, and we know how to anti-differentiate that. Du is 5 dx, or 1/5 du equals dx. Now I return to my original substitution and use it to rewrite the limits of integration. So if x is equal to 0, I get, that tells me u is equal to 5 times 0 plus 1, or 1. If x is equal to 3, 5 times 3 plus 1, or u equals 16. Right. So in my new variable now, I'm working from 1 to 16, 1 over u times 1/5 du. Right. I don't ever have to return to x's because I've changed the limits along with my variables. Okay, I'm all done changing things. So now I get 1/5 times the natural log of absolute u, just some antiderivative. I don't care about the plus c. Evaluated from u equals 1 to u equals 16, excuse me. Right. And so I get 1/5 times the natural log of the absolute value of 16 minus the natural log of the absolute value of 1. Natural log of 1 is 0. I don't need the absolute value here since 16 is already positive, and I get 1/5 times the natural log of 16. Easy peasy.